Hi, my name is Jenny Turner-Trauring, and today I'm going to be talking about how's the mic? Is it okay? It sounds weird to me. Today I'm going to be talking about working with maps, extracting features for traffic crash insights. I'm a volunteer with Insight Lane, which is an open source volunteer civic good project through Data for Democracy. We build tools to help cities and advocacy groups better understand traffic crash risk. We do this by using a machine learning model to predict traffic crash risk given road features. Then we visualize the traffic crash risk. And we can run this on any city that has traffic crash data with geographic coordinates, such as latitude and longitude. This talk, though, focuses on how you can work with maps, but we'll be using Insight Lane's feature engineering pipeline as an example. Briefly, I'm listing the libraries I'm using on the talk for future reference. I'm not going to go through them now, but you can go back and look at this afterwards. This is a Jupyter notebook for the slides, and I'm making it available on my GitHub. It includes some code snippets that I'm talking about, and also some more complex snippets after the fact that you can go back and look at. And the full algorithms for all of this are available on the Insight Lane project GitHub, which I'll link to at the end as well. So say you want to work with maps. You might have one map just for one city. You might have other geographical data, but no map. For Insight Lane, we use cities' open data crash information, which have often are just a CSV of latitude and longitude, but they don't have any map associated with it. You might want to combine geographic data from several data sources, so the crash data and then something else. And you might even want to combine multiple maps together to get features. For Insight Lane, we want any city to be able to use our tools, and so we're using maps from OpenStreetMap as our base map, and then we can add other geographic features onto the map. OpenStreetMap is a free, open, crowdsourced map of the world. It's very widely used. A lot of third-party services use it for a variety of things, such as a base map for visualization, routing applications, and looking at map features. Here's a screenshot of Central Square in Cambridge, Massachusetts. You can see it provides the roads, both the more major roads in yellow and the more minor roads in white. There's a bunch of different features as well, traffic signals, there's a surveillance camera, crosswalks, cafes and banks and other things. And so it's really well populated with a lot of information about your region. OpenStreetMap represents their data as elements. This consists of nodes, which are geographical points, so anything with latitude and longitude. This consists of things like the traffic signals and cafes and other things like that. And then there are ways, which are ordered lists of nodes, and this is how they represent things like streets. So it sort of represents the curvature of the road. Ways are also how you represent things like parks. You have a polygon, you start and you end at the same node, but you trace a line around. And then they have relationships between elements, so administrative boundaries around cities. You can have turning restrictions from one street to another street. And they also provide feature information for their elements using tags, and I'll come back to tags in a moment. So if you've decided you want to use OpenStreetMap and you want to get data out, you can use the Overpass API, which is a read-only API for accessing OpenStreetMap data, and there are a variety of packages you can search for that use Overpass. This is great if you want to get most of the information for a region, but we're going to be talking about OSMNX instead, which is a Python package that allows users to easily download OpenStreetMap road network data. So it throws out a lot of stuff like the cafe information, which you may or may not care about. But for us, we just care about the road network. It's easy to use for downloading the street networks. You can write the resulting road networks out easily. And I have a link to the tutorial here. Again, my slides will be made available. So if you want to use OpenStreetMap or OSMNX to get a city's road network for OpenStreetMap, it's pretty straightforward. You just import it, and you can do something like graph from place with Cambridge, and then you can plot the graph. And so this is the road network for Cambridge, and it's pretty easy to do. But not all cities in OpenStreetMap have their administrative boundaries defined. Cambridge does, but if your city that you want to get street network data for doesn't, then there are other ways you can use OSMNX to get the data. you can get data within a certain radius, or if you have a polygon for the region you care about, you can give that to OpenStreetMap, sorry, to OSMNX. And so we can, again, look at Central Square in Cambridge, and you can just graph from the point. So you've got the center of Central Square and a distance of 175 meters, and you can graph the road network here. The graphing functions I've talked about so far, the default is to simplify the road network, but you might want to actually look at the unsimplified network. What does this mean? It still removes all the nodes that aren't part of the road network, so cafes and other things that are not directly related to driving or walking or biking around. But it leaves, you can see it leaves a lot more nodes in the road network, and some of these nodes correspond to the curvature of the road, or to crosswalks or traffic signals that might fall outside of the middle of the intersection. So depending on what you're doing, you might want the simplified version, and depending on what you're doing, you might want a more complex version and pass in the simplify false. So I mentioned tags before. This is how OpenStreetMap describes features of elements. They're key value pairs. Any element can have a tag, so a way, it might have a tag like a name, which can be the road name, whether or not the road is one way, if it's a cycle track, and if it has a cycle facility, and if it's a lane or a track. And then nodes can have tags as well. The highway tag can correspond to stuff like traffic signals, stop signs, and crossings, which is stuff we care a lot about. And you can have an amenity tag that corresponds to a post box or a cafe. This is by no means an exhaustive list of tags. So let's look at some of the nodes with the highway tag, because this is a feature that we might care about at Insight Lane. Traffic signals and stop signs might be indicative of greater or less risk in our road network, traffic crash risk. So OSMNX returns a multi-digraph, and we can convert it into a pandas data frame. And then we can look at any tag, any node that has a highway tag with either traffic signals, the OSM signals there, or stop. And we'll see that there are 260 traffic signals in the OpenStreetMap data for Cambridge, and there's 7 stop signs. Really? There's more than 7 stop signs in Cambridge. Road networks in OpenStreetMap are generally quite good. So many organizations use it for routing. They need to be good. You can't use them reliably otherwise. But some of the other features in there are only good as the crowdsourcing, and that might only be as good as people actually want to use it. So if nobody's ever said, hey, I really care about the stop signs in Cambridge, maybe no one ever put them in. So that turns out to be a feature we can't use in our model unless we can get the data somewhere else. Can we use the signals? If the stop signs aren't any good, can we rely on the signals? We can figure this out. We can compare it against the open data from the City of Cambridge's municipal government. I feel like Kelly's keynote was a really good introduction here about all the cool things you can do with open data. And Cambridge has an open data program. A lot of cities have open data programs, and so you can go and you can check out all the neat things like squirrel counts off of open data portals. Squirrel counts are probably not useful for road risk. So if we're going to compare the signals, the OpenStreetMap signals to the municipal open data signals, I downloaded a shapefile from the City of Cambridge's open data portal, and then I just used GeoPandas to read in the shapefile. Pretty easy to do. And I see that there are 175 traffic signals municipally provided compared to the 260 traffic signals in OpenStreetMap. So that's not as far off as the stop signs, but it's still a little bit off, and I think we'd like to look at this a little bit further before we use it as a feature in our model. But I have to step back first. So we have the OpenStreetMap network data, and we have ways which broadly correspond to roads, and nodes which broadly correspond to intersections. And depending on what you're doing, this might be enough. Intersections do have a higher crash risk. But for Insight Lane, it isn't quite enough. First of all, OpenStreetMap nodes don't provide a lot of features compared to the ways. They might say that there's a traffic signal there, but it won't talk about the width or the one-wayness of the road coming into the intersection. And also, crashes might not happen exactly at the point where the two roads cross. And it doesn't handle complex intersections either. If you have two intersections right next to each other with two different nodes, then maybe you want to treat that as one system that drivers are passing through. that people are passing through. So we're going to use a different abstraction, this notion of segment, which expands the concept of intersection, and we're basing it off an algorithm by Azabea, which I link to if you get my slides. So first we need to do a little pre-processing. We saw earlier that you can turn OS7X output into a GeoPandas data frame. You can also write the OS7X output to file. You can use the function savegraph shapefile, and that outputs it. I don't output this here, but in a hidden slide from the Jupyter Notebook, you can see me doing that. And then we post-process to GeoJSON format, because that's how InsightLane internally handles our maps. Once we post-process this, we can read the GeoJSON map in, and then roads are OpenStreetMap waves, and intersection points are the remaining nodes after we do the OS7 simplification and after we drop dead ends. But we want to treat intersections as sort of a bigger space than just that point. So what we do is we create a 20-meter buffer around each intersection, just draw that circle, and we use Shapley's buffer library for this. Then some of these are more complex, and so we merge these together. And any overlapping buffer we merge using the Shapley library's union function. And we take all the road segments inside those bubbles, and they are the intersection segments. And so you can see the sort of straightforward intersections there, and more complex intersection here. And then the resulting non-intersection segments are just all the road segments that are left over after we exclude the intersections from the previous slide. All right, so we've defined this road segment. When you're working with multiple geographic data sets, you need a framework against which to compare the data sets. And so ours is this road segment abstraction. Once you've done that, you need to make sure the data sets have the same coordinate reference system. I'll talk about that in a moment. And then you want to visualize your data, probably. It can be a good idea to make sure nothing weird is going on with it. It'll help you debug. And I recommend if you're just trying to understand what's going on and this is an option for you, work with a city or a region that you are familiar with. Cambridge is my example because I live there, and so I can get a good sense of whether things are behaving as they should be. So our example is comparing the traffic signals from the City of Cambridge's municipal data against the OpenStreetMap data. So first, you need to make sure that they have the same projection. When we're working with maps, they're flat and the Earth is spherical-ish. And so you need a way to project all of the things on the surface of the Earth onto a flat surface. And when you do that, you're going to be introducing some sort of distortion. You can see the picture of my daughter introducing some distortion into that ghost on the pumpkin. And since you're introducing distortion, you need to have it be a consistent distortion that you're introducing. And so that's why you need the same projection for everything you're working with. A lot of data you'll see when you're looking at open data will be in EPSG 4326, which corresponds to sort of what we think of as latitude and longitude. And you typically see data stored in 4326, but might be displayed or worked with in 3857. So you just always need to check your data set's coordinate reference system. And this is a really great reference below to learn more about projections because it's actually a very complex topic. So we need to reproject our data. I'm going to give two examples of how to reproject data on the Cambridge municipal data set. The first is going to be using GeoPandas. It's pretty straightforward, really. You can use the toCRS function to give it the projection that you want, and then you just have to make sure that you're updating the data frame's coordinate reference system to be whatever it is you're converting into. GeoPandas is very straightforward to use, but I found that it can be pretty slow on larger data sets. And so for InsightLane, we use PyProj. PyProj, you need to know what the initial projection is. So we'll check out this municipal data, CRS, and it's 2249, which is not 4326. It's the Massachusetts mainland projection. So always check. And then PyProj has a transformer object that you can give the starting and the ending projection and use that to transform the coordinates. It's a little more complex when you're looking at lines and polygons than it is with points, which is why if you're just playing around with smaller data sets, GeoPandas might be a better option. And then I wanted to make sure that this was working, so I just checked to see that the data frame from the GeoPandas projection was the same as the data frame from the PyProj projection, and they are, so that's good. All right, so we projected our data. Behind the scenes, I did the OpenStreetMap data as well. I output it to file behind the scenes, and then I use the QGIS GUI to visualize most of the time. And so the picture there is just a portion of the signal data and the segment data for Cambridge in the QGIS GUI. The outlined layer lines are the OpenStreetMap traffic signals, and the dark circle is the municipal signal. So we'll see often that features in one data set might be close to, but not identical to the other data set. These don't line up exactly, but they do correspond to the same intersection. So what we want to do is standardize the two data sets, and in our case, that involves finding the closest road segment, our intersections and non-intersection segments from before, and figuring out what the closest segment is to all the signals. Now you can do this by iterating through all of your segments and all of your points. That's very slow, so I recommend using the R-tree library for indexing spatial things, and that speeds it up a lot. The code for all of this mapping points to segments is in the Jupyter Notebook. You can go back and look at that later. And then Inset Lane uses this technique of mapping points to road segments to standardize any point-based feature that we want to add to our model. All right, so find nearest is in my Jupyter Notebook, but you're not going to see it at the moment. So we're just calling find nearest on both our municipal data and our OpenStreetMap data. And then we'll see that we've got this near ID, which is the segment ID associated with this particular point. Great, so how does this work? Well, most of the signals, it turns out, are pretty well aligned and matched to the same segments. And sometimes you'll see that OpenStreetMap has several segments on an intersection. There's only one municipal signal, and that seems to be because OpenStreetMap may be recording every place there's a light pole with the traffic light on it, and Cambridge is only doing it for the intersection as a whole. But there are still some segments that match only with the signal in one data set and not the other one. So we can find the signals unique to each data set by looking at the ones that Cambridge has a segment ID, but there's no segment ID for OpenStreetMap and vice versa. And we'll see that there are 17 signals that are in the municipal Cambridge data that don't appear in the OpenStreetMap data, and 41 extra signals in the OpenStreetMap data that don't appear in the Cambridge data, the municipal data. So let's dig into this even a little further. We'll output the mismatching data sets to file. We'll visualize them again. And this time, I wanted to know what was going on, and I happened to look at just the intersection segment and not the combined segments, and discovered that all of those OpenStreetMap traffic signals fall outside of the intersection, and so that is why we're seeing more signals for Cambridge in one set of segments and more signals for OpenStreetMap somewhere else. So this may mean that our abstraction isn't great. I looked at the Google Street View version of this intersection and found that it's a really big intersection with very wide lanes, so maybe our 20-meter buffer isn't big enough. Maybe we want to expand our intersection segment concept for complex intersections. Or maybe we want to say that signals really should fall at intersections, and instead of mapping them to the nearest segment, whether it's an intersection or a non-intersection segment, we want to map it to just the intersection segments. So that's something that I'm not going to talk about now. I'll have to think about for later. But this still accounts for many of the mismatches we see in our data sets. There's some remaining ones I was looking at. If the remaining ones were in OpenStreetMap but not in the municipal data, I could visualize them in OpenStreetMap directly. So you can search for nodes or ways. And you'll see that this is a blinking traffic light, not a standard yellow, red, green one. And so Cambridge is not including that. And so that explains that. Maybe we should filter out the blinking signals from our data set. But I think on the whole, we've been using the OpenStreetMap data. I had actually not analyzed it this carefully before when we use it as a feature. I think it's probably decent for what we're using it for, although I should think about the size of the intersections. And so that's just one way you can look at combining two different data sets and trying to understand what's going on. So what have we learned? First of all, OpenStreetMap might not match municipal data. It might be way off, like the stop signs, it might be a little off. You might be interested in updating OpenStreetMap for your city of interest. This is definitely something you can go and do. If you find stop signs important to you, you can go ahead and add them. You might be able to find a stop sign data set for your city and add it automatically, or maybe you have to be more sophisticated and figure out where everything is. I wouldn't recommend that. And it's also a good idea to check your data to see if it makes sense. And in our project, as in any project, there's a lot of data limitations. Some of the geographical data limitations you might see are that, again, OpenStreetMap is internally consistent across cities for the most part, but it may be incomplete. Municipal data can also be inconsistent either within a city or between cities. So the projections can differ, maps can be represented differently, and also cities collect data, and that can be in all sorts of crazy different formats. The city of Boston collects automatic traffic recordings, and they put it in a spreadsheet. And the spreadsheet, there's like 3 different spreadsheet formats, and they sort of count by hour. Then it depends on which spreadsheet you're looking at, whether it matches up. And so you have to write this like very complex custom code to be able to process stuff like that. So you might choose that maybe it's not worth adding it, or maybe it's worth your time to pre-process the data, but formats can be quite a bit different. All right, so Insight Lane uses these, any point-based feature we can add to our model by using the same technique we looked at before. So this can be the OpenStreetMap data. You can get data from municipal data. Parking tickets might be interesting to look at. Maybe street trees, maybe squirrels, who knows. And some cities also make their publicly crowdsourced data, like 311 data, publicly available, and maybe you'd like to look at that for your project. And you can also add features from other maps to the OpenStreetMap, or just combine 2 different maps. When we started this project, it was just on Boston, and Boston gave us a municipal data map set for this, and it had a bunch of features on the segments, like speed limit, which was well populated. OpenStreetMap's speed limit is spotty. With annual average daily traffic, the type of road, and a bunch of other useful features. When we expanded this project to include any city and use the OpenStreetMap data, we didn't want to lose these features. So how could we combine the maps that cities might give us with the OpenStreetMap maps that we're generally using? Well, it's tricky. Maps don't always line up perfectly. This is a picture of OpenStreetMap and the Boston municipal map together. The light blue line in the middle is Boston's municipal map, and the 2 lines around it are OpenStreetMap. The Google screenshot shows that OpenStreetMap is treating this as 2 one-way roads because of that median in the middle, and Boston is treating this as 1 two-way road. But really, it's the same road, and we'd like to be able to use the features from the Boston map. So how can we combine this? So we're going to have to treat intersections and non-intersection segments differently. First thing we'll do is look at intersections. I have this little fake one-way street here because it's just useful for the example. First, we create a buffer around the OpenStreetMap intersection segment. Then we create buffers around all of the municipal intersection segments. We just look at the buffers that overlap. Again, we'll use R-tree to find the ones that are nearby. And so we have 2 overlapping segments here. And the one in the middle, the one associated with Boston, the intersection, overlaps the OpenStreetMap buffer entirely, and the fake one-way intersection doesn't. So we choose that as the match. For non-intersection segments, it's similar, but you see some differences. You might have sort of 2 short segments, the 2 blue lines, that both correspond to the black line. And you also might have other parallel lines that are nearby. So what we do is we do a buffer again around the segment we're trying to match, so the black line here. And if we do a small buffer, we'll see that these 2 lines are within it, and we'll just take those lines as the matches. But if those lines weren't there, we would then expand the buffer and a larger buffer on this black line would capture the further out line. We would use that as the match. And we get about low to mid 90% matches on the segments between Boston and the OpenStreetMap segments. So it's pretty good for adding features. All right, so now you can load and process map data. Yay. The source code, again, for this presentation will be linked at the end of the talk. I encourage you to go and play around if you're interested in understanding this a little more deeply. And then what do we have left to talk about? First is to not forget to think about equity. And second, I want to show you InsightLane's crash model because we're very proud of it. All right, so it's a common data science pitfall is doing analysis on data that inadvertently contributes to inequity. You always have to think about how this might happen and what you can do to avoid it. So Boston, for instance, has a neighborhood slow streets program, and this is traffic calming on a neighborhood level. So if you're not familiar with traffic calming, it's engineering changes to the road so that drivers go more slowly. But if you traffic calm on one street and everyone's going slowly, they might switch over to the next street over, and that's frustrating to a neighborhood. And so Boston wants to treat neighborhoods on a holistic level and slow the streets in general so you're not seeing those impacts. And so neighborhoods in Boston can apply to participate in this. And I'm not sure about the details of the application process, but it includes letters of support from community groups and maybe some public meetings and things like that. And once they have the applications, they evaluate them based on objective criteria. And this includes a bunch of things, including high crash areas, schools, number of children living in the neighborhood, number of seniors, and proximity to transit. So they are objective criteria. These things are either true or false, or there's numbers associated with them. And some of them I think are good features. You probably want to reduce crashes in areas that have a lot of dangerous crashes already. I could see a good argument for wanting to reduce crashes and make it safer around places where kids are walking to school a lot. But proximity to transit is one that's tricky because it might mean that people are walking a lot more because they're close to transit. But historically, marginalized communities have had less access to transit. So if you're using this as a feature to make a decision based on who gets slow streets, are you making inadvertently biasing it towards a decision that means that marginalized communities get slow streets less? And so Boston, I think, is aware of this, and they have been tweaking their model. But this is just something to think about whenever you're doing data science where you're making decisions. How would this impact people in ways that we might not want it to impact? And here is the InsightLane crash model. We feed features into a machine learning model, and it calculates the crash risk, and we can display the results in map form. The darker lines are higher risk, and the lighter lines are lower risk. And this is the bike crash risk map because many cities provide what the mode or the person, vehicle or pedestrian or bike type they're using. And so we actually filter these out, and you can also, I'm not showing it because I think it muddies the map for this presentation, you can click the show crashes button and it will display those crashes for bikes in this case. And we also show the highest risk segments as predicted by our model for the city of Cambridge. That's it, thank you. You can email me. You can find my presentation on my GitHub at presentations. And if you're interested in getting involved, there's two ways you can get involved. You could be interested in modeling your own city's crash risk. We don't currently do New York. We have about 5 cities that we have on our website, or maybe some other city that you're from, you really want to visualize the crash risk, so you can do this. You can also get involved with us and volunteer to write some code with us and build up our product so it can be more useful. So you can check our website with the visualization from the previous slide at insightlane.org. And our GitHub is there, and you can go to it and it'll talk you through how to run our pipeline for your new city or how you can get involved with us. Thank you. Questions?
Any questions? You said one part is making sure the data analyst doesn't contribute to inequity. So How do you check for that? Do you check as their team if there are any like certain groups that they're concerned of? Do you talk to your stakeholders? Because we're not aware of our blind spots. So how do you become more aware of your blind spots, and how does your team do that?
That is a really great question. I don't have a great answer for it. I think that the more people you can talk to, the better. The more broadly you can make your project available to different stakeholders, the more likely you are going to be that someone will raise an issue. I think there's also some great books to read about inequity. Kathy O'Neill's Weapons of Math Destruction, I think. That was one that I enjoyed and thought it was useful. And like we've also found out, longer answer. There's a thing that some cities have called a Vision Zero portal, which allow people to go and enter their concerns around intersections or other areas and saying this is dangerous because people speed or there's not enough time to cross the road. And we can use that as a feature, and in fact we do. I think at this point we're still doing a lot of exploratory data analysis and no one is actually making decisions based on our product yet. But when we talk to Philadelphia, and they do, some people in Philadelphia do use our product to visualize things. They didn't want to use the Vision Zero data. And I think that's a reasonable decision to make, because who is entering the data? Who has the time and the smartphones or whatever to like actually spend the time saying, this intersection, it's no good. Are we collecting data in a fair way? So I think the more people you talk to, and just make sure that you're also listening to a variety of groups. But it's a hard question.
Thanks again also for calling out that piece of it. But do you think that graph spatial map-based data is like particularly prone to bias? I think, I guess in your opinion, as someone who's been working on it more closely, I feel like we've seen how zip code is obviously a very problematic variable in a lot of contexts, those significance examples, but I think like in a couple of the books you mentioned, like, I don't know, I just say it's in your opinion.
This is my domain of expertise, so I can't speak about the other domains. They may be hugely problematic in ways I'm not familiar with. I think probably. I think that because we have such heavy segregation historically, and the built environment changes based on like where you are, and that is contributed to by segregation. I think yes. I think geographic data it can be a really hard thing to make equitable, and so extra good to be aware of for that.
Any more questions? Oh, great.
Hi, thank you so much for your talk. I don't know if this is a question as much as it is a comment, so please excuse. But I feel like this idea of inequity is going to be a recurring theme coming up. I think it was mentioned in the first keynote. And to me, it seems like a very obvious solution that looking around in a room, it still needs work, is why not just hire people from marginalized communities? Like, I grew up without a car, we were that poor. I can tell you how much it sucks to go down the street next to like a 6-lane street, not even a highway, right? And so if you want to talk about inequity, I mean, it seems like such a simple thing to just like, hey, why don't we get a bunch of, poor black and brown and indigenous people in our data science teams? Like, and again, I think that's more of a comment.
Can I just?
Than just like a question.
Yes.
Like, that's going to be a recurring theme here, given the first two talks we've been to.
I think that's a great point, and I probably should have been more explicit. I don't work for a company that's as small. I mean, we should be doing a lot of outreach ourselves, but I think that there's a lot to be said for examining hiring practices and seeing what we can do in that direction. And if there's not an unconference on that, do you want to propose an unconference on equity?
I make a lot.
Okay.
I think there was one more question in the back. Phil?
Thanks very much for your talk. I was just wondering if you incorporated time series data at all, or if you were basing your projections on aggregates.
When we started this project, we were looking at doing time series, and we looked at some weather things and some time of year things, and our data sets are pretty small, and so we just found that that was not, at the point we're at, it was hard to deal with, and so we removed the time data. But I think that's actually a really good point, that the day after daylight savings time, the commute day, that's a higher traffic crash risk, and so there's definitely things you can get from that.
Anyone else? I think we have 10 minutes.
Okay.
Hey, thank you. I was wondering, you said that for now this is mainly exploratory work, and I was curious to know what your opinions were on what possible applications would be and how you see this going forward.
I guess I shouldn't have used the word exploratory. I think we're a little farther along that line, and I sort of hope so. We're working a little bit with the city of Melbourne to visualize crash risk, but we're still looking for cities to get involved with, and also I think advocacy groups who want to better understand their traffic crashes, and so maybe they can more effectively lobby their cities, I think are a good user for this. I think the big limitation with many data science limitations is if you have this black box machine learning model and you're saying this road is really high risk and traffic departments don't want to make a decision based on our say-so. So the next thing we're interested in looking at is saying why our model says that it's high risk, and so then they can look at it and they might be more willing to make decisions based on that.
There was one more, and then I think that's...
How do you manage outdated maps, especially in the city environment? There's a lot of road closures, new buildings popping up, and it might be hard to rely. Do you rely on the kind of map that you're given?
Since we're using OpenStreetMap as the base map, I think we're assuming that it gets updated with reasonable frequency, and we do occasionally pull it again. But municipal maps can definitely be out of date, and if we're looking at some of these features and they don't map to something because the road doesn't exist anymore, I think that is a real risk. If anyone wants to talk to me afterwards, if anyone wants to talk about open data or maps, I would love to hear from you. Thank you.